Now we're going to talk about instantaneous rate of change. Some other ways to say instantaneous rate of change would be for me to say the slope of the curve at a point, or I can ask you for the slope of the tangent line at a point. And so what we're really doing is finding the slope at one point versus the average rate of change where we find the slope at two different points. The formula we use is the limit as h goes to 0 of f of x plus h minus f of x all over h. And we call this the difference quotient. So you'll hear me reference those terms when I want to do the limit as h goes to 0, this formula. So the difference quotient. Let's start out with our first problem, which is the instantaneous rate of change algebraically. So I give you a function. I'm going to ask you to find the instantaneous rate of change at x equal to 2. So that is the same thing as finding the slope of the tangent line at x equal to 2, or the slope of the curve at x equal to 2. So let's start off with the limit as h goes to 0 of f of 2. So I'm substituting in 2 for x, because that's the value they gave us. Off to the side, if you're having some trouble with these problems, remember what I do is, a little mark here so we don't get confused. So what I do is I find f of 2, which would be negative 2 squared minus 4, or sorry, plus 4, excuse me, 0. And I also find f of 2 plus h, which is the same as negative 2, that's not supposed to be an x, 2 plus h squared plus 4. You're going to FOIL this, 2 plus h times 2 plus h, and we get 4 plus 4h plus h squared plus 4. Distribute my negative, negative 4 minus 4h minus h squared, and then don't forget your plus 4 in the back. These will cancel, and you get left with negative 4h minus h squared. So I'm actually going to use this part right here in red, and that's going to be my f of 2 plus h right here. And this value in pink is f of 2, and I'm going to substitute into this value. So in red, let me start out in blue to make my limit as h goes to 0. Fraction bar, h, the minus sign, and in red I'm going to put in my negative 4 minus h squared. And in pink, I'm going to put in my 0. And so really, if you look at it, that's going to cancel, and I just realized that's supposed to have an h. We're going to simplify this guy by factoring out an h in the numerator. And we get that the limit as h goes to 0 of negative 4 minus h, this value goes to 0, so we're left with negative 4. The slope of the curve, the slope of the tangent line at x equal to 2 is negative 4. So let's look at what that means in terms of a graph. So at x equal to 2, here's your point, 2 comma 0, which we found, f of 2 was 0. What it says is if I draw a tangent line, so if I draw a line that seems to be tangent to the curve, I bet you that my slope is going to be very close to negative 4. Now, my drawing, because I'm guessing what the tangent line kind of looks like, it's not going to be perfect. But I can show you that the slope of this line, what we found was that the slope of the tangent line should be negative 4. If you look at my tangent line, remember we said it's like a seesaw that's balanced on the curve. This kind of angle and this kind of angle should look about the same on both sides. Now, slope of negative 4, I'm going to go up 1, 2, 3, 4. I'm going to go left 1. And that does give me a slope of negative 4. And if you notice, my tangent line actually was almost perfect. So the slope of this line is negative 4. You can see it graphically, and we did it a second ago algebraically. So what I want to do is actually kind of ask another question, which would be find the equation of the tangent line at x equal to 2. And what are the two things that we need when we find the equation of a tangent line? We need the slope of tangent line at x equal to 2. And how do we do that? We use the difference quotient. We do the limit as h goes to 0 of f of x plus h minus f of x all over h, which we just did, and we found that that value was -4, so I'm not going to redo that. The second thing we need is a point. That's always the easy part. They gave us x equal to 2. We found that the y value was 0, and therefore, put those two things together, we find the equation of the tangent line to be y minus 0 is equal to -4 times x minus 2. And if you simplify this to be slope-intercept form, and I'm going to have to go over this way, slope-intercept form would be y is equal to -4x plus 8. And if you look at this graph, you really would see that the y-intercept would be 8, because you would go up 4 more and go to the left one, and you would be at a y-intercept of 8. The next question that I could ask is the equation of the normal line. And so let me actually insert a page, because I don't think that's set in here. The equation of the normal line for f of x is equal to -x squared plus 4. And we want to do the normal line at x equal to 2. Well, we would be stuck doing the same thing. We would first have to find the slope of the tangent. And how do we do that? We would have had to go through this whole limit as h goes to 0 of f of x plus h minus f of x over h. And remember, we found that that value was -4. Second thing you would have to do is find the slope of the perpendicular line, which is opposite reciprocal. And so that would be the reciprocal is 1/4. Opposite sign would make it positive. And the third thing we need was the point. It's the same point that we're using, 2, 0. Therefore, the equation of the normal line would be, we'll do that in red, y minus 0 is equal to 1/4 times x minus 2. And the slope-intercept form of the line, 1/4 x minus 1/2. And so if I go back over, I can actually show you that line, and I'll do that in orange, that if I wanted to make this to be normal, I could go down 1, left 1, 2, 3, 4. So that would be my normal line. And you can see that the y-intercept is about 1/2, and I was kind of guesstimating, but there's your normal line. So the normal line is perpendicular to your tangent line. And so graphically, anywhere I put a tangent line, that's what an instantaneous rate of change is. So if I put one here to make the seesaw balance, it's actually going to be a horizontal tangent line. Same thing here. It's a horizontal tangent line. If I put one here, because the line itself is almost straight, the tangent line looks like the curve itself. And that happens anywhere where this cubic curve starts to look straight. But if we're doing a tangent line where it's not so straight, it'll be obvious that it's not going to look exactly the same as the curve. Remember, when we say the word curve, it actually means the graph. So we call linear curves, those are just straight lines, but you'll hear me say the word curve instead. And hopefully I